Good morning. We have already discussed in my previous lectures on solar cell and photovoltaics devices. This was the first module of this lecture series, and the second module was thermoelectric generator. Today, we'll start a new topic, that is using hydrogen as energy storage and for supply to energy to various equipments, electrical equipments and other devices. So, if we look at the situation presently, as I already mentioned in my introductory classes, that we are in a great problem with carbon emission. So, most of the sources of energy, whatever is these days we use, they produce a lot of carbon. So, therefore, what happened that lot of pollution is what we see in the environment, and by 2050 people think that we should have the energy resources which should be completely carbon free. This is a kind of goal which present day science and technology has already set up, and then people have to work in this direction. So now if we again consider the sunlight as a source of energy, and we have already discussed that when we use sunlight as a source of energy, how it produces electrical energy by photovoltaic devices. Now this sunlight, the energy of sunlight to photovoltaics is direct conversion from the energy of sun to, or light energy to electrical energy. Now question is, can we convert this light energy to chemical energy? Why this is required? Because if you look at various geographical locations, there are some places where there is hardly any sunlight for long duration, even for a day or for a month, even for several months, there is hardly any sunlight. So even if we want to have a photovoltaic technology or solar cell technology in those places, it doesn't work for the rest of the time when there is no sunlight. The essential requirement of solar cells is the sunlight should be good enough or strong enough to generate electricity. So now what is the alternate way? What people think what one can do? Suppose for 5 months we get sunlight and we get electricity using solar cell. Now rest of the time, from where do we get energy? If I just remove for the time being all the conventional sources of energy, because they are having problem with lot of carbon emission, they are also getting depleted, all the sources of conventional sources of energy, and therefore we have to use solar energy. Now rest of the time of the year, sunlight is not there. So what one can do, one can store this energy. So whatever electricity you produce, you store this electricity in some device, storage devices. Now again question comes, what are the storage devices? So one important storage device is battery, we all know. But that we cannot have a battery for large scale electricity generation or electricity distribution. Okay, we can have batteries for this is for some home appliances or something, so we can charge the battery, keep it for home appliances. But remember that the battery is also a huge problem with chemicals and also stability issue. So it seems that if we want to store energy, as you know, or the sunlight energy by PV conversion and store energy in the battery, doesn't look like a very feasible choice or option. So that is the reason why we have to think about the storing energy in the form of chemical bond. Okay, so we have to involve little bit of chemistry here in order to understand how to store energy in in chemical bonds. So the main idea is there. So suppose I have sunlight and I produce some chemical. Suppose here hydrogen. Okay, hydrogen is very abundant material, it's a very light material, and it can be stored. So huge amount of hydrogen can be stored and which can be used. We all know that hydrogen is used as fuel for long time. It is not a recent concept using hydrogen as a fuel, although we do not see hydrogen fuel in many places, but slowly people are going towards the hydrogen fuel economy. And therefore, the idea is, can we store everything as hydrogen? So this is the basic motivation of this particular topic. So in this topic, we will discuss PEC water splitting for hydrogen production. So just to give you an estimate that the heat energy that is produced on burning 1 kilogram is around 147 megajoule, which is higher than that of fossil fuels, with the energy yield of gasoline being 48 megajoule per kg and that of diesel being 44.8 megajoule per kg. So that means if we burn 1 kg of hydrogen, we really produce huge amount of energy. Okay, so now we come to a question that whenever we talk about hydrogen production, these days probably you have heard that green energy, green hydrogen. The meaning is that the carbon free emission. Okay, so why green hydrogen? The first thing is that the green hydrogen is zero emission, there is no carbon. Why? Suppose I split water, H2O, which is huge amount is present everywhere. Okay, and I split it. If I split H2O molecule, that is water molecule, I produce hydrogen and oxygen. So I don't have any, the carbon here involved if I can split water. Okay, so that means in this entire process, I don't have any carbon emission issue. All right. So the first point is, as I mentioned, is zero emission. All right, that is the first motivation for going towards green hydrogen. And second is energy storage. What do you mean by storage? So you can see the huge tank, the hydrogen tank. So if I can produce huge amount of hydrogen, okay, by some means, sunlight could be one, there may be other approaches also, but if I have the capability to produce huge amount of hydrogen and I store all hydrogen in the tanks, big tanks, okay, and keep all these tanks, and then I use them as fuel. like we store oil and then we, use them for fuel for automobiles or many other things. So similarly, I have hydrogen tank from where I use hydrogen and use them as fuel, use it as fuel. Okay, so that means I basically what I have done, I have stored energy in the form of fuel or hydrogen. So the second point is energy storage. Third is very important. So one is I have a production of hydrogen with zero emission, and then I store hydrogen in big tanks if I can. My production capability is good enough. And third is transport. Okay, so you can see that all green vehicles, that means the vehicles which are only fueled only through hydrogen. So when these vehicles run, they don't emit carbon. It is completely carbon free automobiles. Although we don't have, we can see somewhere very specific locations or some specific purpose people use automobile with hydrogen, but we can think about the future automobile completely based on hydrogen. Okay, so that our entire transport system, be it a small smaller transport like our day-to-day use automobiles or vehicles, or be it a very large transport like railways, okay, or ships. If we can fuel everything through hydrogen, then we reach to our goal. That is what, by 2050, the aim is completely carbon-less, carbon-free environment. Okay, so this is the motivation behind this. So if you use this particular, the idea, or if we can make it realize, if we can realize it in practice, then it would save about 830 million tons of CO2, the achievement in our entire science and technology. So if we look at the global demand for hydrogen for fuel has multiplied, it is almost like tripled since 1975, and in 2018 people show that it is almost reached to a level of 70 million tons a year, and now it is even more. So that means there is a huge demand of hydrogen. Okay, in fact there are many countries like USA, various countries of Europe, Japan, China, they are all going towards it, the hydrogen based automobiles. And Japan has already flagged this, that saying that we will be having a hydrogen economy in future. Okay, that means completely pollution free environment in future. So this is our goal. Now when we talk about green hydrogen, what essentially, or green economy or green environment or green energy, what essentially we mean, that if you look at this flow chart, this is a renewable electricity generation process. Okay, we are all aware about it. Okay, then we get this energy or the electricity to some kind of electrolyzer. Okay, then we go to what is known as hydrogen electrolyzer, H2 electrolyzer, which produces hydrogen. All right, and then we store this hydrogen in various tanks. You can store huge amount of hydrogen, it is very light. Okay, and then you can transport also easily. So now the hydrogen production and hydrogen distribution, and then you use it for everything, be it for an industry, or it is for a ship, or for a bus, for automobiles, for vehicles. Everywhere you use this stored chemical energy. So I have started this point that if some energy can be converted to chemical energy, and this chemical energy, stored chemical energy, can be used for all purpose, then we have a completely an economy which is only based on that uh, process. And if hydrogen is the fuel, or then more specifically green hydrogen is the fuel, then we are in green economy or green environment. Okay. So the advantage is that it is 100% sustainable. 100% sustainable. When you talk about 100% sustainable, that means that we do not have any problem related to carbon emission or pollution generation. Okay. So therefore it is 100% sustainable. Second is it is storable. Hydrogen is storable. As you can see, one can store hydrogen, one can also transport hydrogen very easily. Okay. So once we store, we can use it also. And third is it is versatile. Versatile in the sense that you can use it for many purposes. I have shown you, you can use this stored energy to suppose in industry, or to in ship, or automobiles, all vehicles, all appliances, every appliance. Okay, that this stored energy can be used. Okay, so it is a versatile source of energy. And therefore, as I mentioned, some countries have already decided they go for completely hydrogen society. Okay, so that will change the face of human civilization if one can do it. Now the question is how to produce hydrogen. This is a big question, because I already showed you what is the the demand of hydrogen, and that was almost 6 years back, which I have shown. The demand now is very high. So if our demand is very high, we should have also production. So we should know what are the production pathways of hydrogen. So generally there are three hydrogen production. One is from fossil fuel burning. Second is from biomass. This is also known as biomass gasification. Okay, and the third one is electrolysis. These are three important the procedure by which people actually produce hydrogen. And it is not a new technique. People are doing it for quite some time. For long back it is going on. The electrolysis is relatively new. And then one addition to this electrolysis, which is part of this particular topic, is photoelectrolysis. Okay, or photoelectrochemical water splitting. This is the main topic of this particular lecture. So what is actually the fossil fuel burning? Fossil fuel burning, that when we talk about fossil fuel, we remember what are the fossils. Fossils are basically this all animals and plants which are already died and they are buried, and they have generated a fossil. So okay, so there are several pathways to to produce hydrogen from using this fossil fuel burning. One is called synthesis gas, that is a mixture of hydrogen, carbon monoxide, and a small amount of carbon dioxide is created by reacting natural gas with high temperature steam. Okay, and now the carbon monoxide is reacted with water to produce additional hydrogen. So this is probably the oldest method by which people have produced hydrogen, and one can produce large amount of hydrogen, but this hydrogen is not a green hydrogen, because you know, as soon as you do this fossil fuel burning, you have all emissions of carbon and carbon compounds. Okay, you produce hydrogen in a large quantity, but you have carbon also associated with it. So I not mark it as a green hydrogen production, okay, but what I try to, you know, understand here, what are the method by which one can make green hydrogen. All right. So another method is, as I mentioned, biomass gasification, that also people use, and that is actually the solid biomass can be converted to gas. That is called biomass gasification, but that is also not pollution free. Okay. So the third method is electrolysis. So what we do in electrolysis process, so we have, so this is a typical, you know, the electrolysis setup. So you have water along with some, you know, electrolyzer, some chemical which is there inside this chamber, okay, and then you have electrodes, a cathode and anode. You pass current, okay, or apply high voltage, so that the electrolyzer or the chemical inside this electrolysis setup gets ionized, and they flow towards different electrodes. All right, and then one electrode you produce oxygen, and another electrode you produce hydrogen. So what you do by electrolysis process, you split H2O to hydrogen and oxygen. Okay. All right. But this process actually involves huge amount of electrical energy at the input, because you have to, you know, ionize or pass a current to the electrolyzer, and therefore you already have an input energy given to that. So this means that this is okay, one can produce green hydrogen using simple electrolysis, but it seems that the method is very costly. Okay. So one particular problem which comes in the electrolysis process is the method is very costly. Okay. So this is a drawback. Second is, when you use the fossil fuel burning process or biomass gasification, you produce huge amount of hydrogen. Particularly fossil fuel burning gives huge amount of hydrogen. But here, as it is a chemical process, you do not have a huge hydrogen yield. Okay. So the hydrogen production is relatively, hydrogen yield is low. Okay. And the third issue is, you need an input electrical energy. So we have to overcome these, you know, the challenges. We have to make this technique cost effective. Second is, we have to have huge amount of hydrogen production. Hydrogen yield should be high so that you can store large amount of hydrogen for future purpose. Okay. And there should not be any input electrical energy. How it is possible? If I do not have an input electrical energy, then how can I, you know, break the water molecule is the question and produce hydrogen and oxygen in two different electrodes. Okay, so this was a question for a long time, and people could solve this problem. Okay, so now how is this process? How it happens? How one can, generate hydrogen and oxygen? So I will just write down the basic equation. Suppose I have an electrode. Okay, I give it a name as photoanode. I have another electrode. This is a metal. Say I use platinum as a metal. Okay, so suppose this is semiconductor, this is metal. Okay, so once we have semiconductor, we have, the conduction band. We have valence band. Okay, we should make this conduction band, free from this. So let me again draw. So this is a semiconductor, this is photoanode, this is semiconductor. I have a metal. This is a platinum. This is also known as counter electrode. Okay, so I have this conduction band. There is no electron in the conduction band, it is empty. I have valence band which is full of electrons. Okay, I have certain Fermi level, and then this is all H2O and containing chemical, suppose KOH. Okay, this is a good chemical which is used, and then sunlight is falling, H nu from sun. Okay, so photons are falling. All right, so this photon is absorbed by the semiconductor or by the photoanode. Okay, so once it absorbs, one electron jumps from valence band to conduction band and it becomes free. So one hole is produced here. One hole is produced here, H plus and E minus. So what is happening? That photon actually interacts with this photoanode and it produces H plus, E minus. This is the first step. Now this H plus, it actually it splits now water. It becomes H plus plus electron plus oxygen. Okay, I can write it half oxygen. Okay, and then C2H plus. All right, so I already produced oxygen here. So I have a oxygen evolution reaction, OER. Okay, so at the photoanode I have oxygen evolution reaction, OER. This actually this whole interacts with H2O and generates oxygen at the photoanode or oxygen evolution reaction. That is second step. And third step, produces 2, or if I write 2H2, then to 4H plus and 4E minus. This electron goes here and then it produces hydrogen here. at the counter electrode using this reaction. Okay, so I have OER in the photoanode, that is oxygen evolution reaction at the photoanode, and now I have hydrogen at counter electrode, and that is called hydrogen evolution reaction, HER. These two are extremely important, and that is what is known as photoelectrochemical water splitting. And this hydrogen is completely, I should mark it with a green. It is completely a green hydrogen. Okay, so this is a very simple process. I just use sunlight and then use the OER and HER reaction, and HER reaction gives me green hydrogen. Okay, so now coming back to the chemical reaction. So again, I try to compare it with photosynthesis, which is already there in the nature. So you can see this is photosynthesis. So here sunlight falls and the plant actually absorbs sunlight. The leaf, green leaves, absorb sunlight as I mentioned, and then it undergoes this reaction. Carbon dioxide interact with water and then light, and then it produces glucose. Okay, C6H12O6. This is actually a very big chemical molecule which is stored as energy, or you can say it is a kind of food. It also produces oxygen. So almost similar which I have done in photoelectrolysis or photoelectrochemical water splitting, where I split H2O, okay, with the help of light, and then I produce oxygen and hydrogen. Okay. So this was a very interesting, the discovery which was made by, first reported in 1972 by Fujishima and Honda. It was published in Nature, and it is one of the article which is being highly cited, probably the one of the article which is having maximum number of citation, because as soon as people realized that one can split water and produce hydrogen or oxygen, this hydrogen is completely green, then the entire, the idea that the green hydrogen can also be produced, and without having the input of electrical energy which is generally required for the electrolysis, one can only use the energy from sunlight and split water. Okay, so if you remember the 3 points I mentioned as drawbacks of hydrogen production by electrolysis, the first point was costly. Second point was that we need to have some electrical energy as input. Okay, and third point was hydrogen yield. The production of hydrogen is less. So at least one point we could able to address here, that we don't need any electrical energy as input. Our input energy is only sunlight, and we split water only using the energy from sun. Okay, now still we have these two, the issues which need to be addressed. Okay, so the one issue is hydrogen yield. That is extremely important. Okay, how to improve the hydrogen yield. Okay, I will come to this point as we go along in this talk. We will understand how to enhance the hydrogen yield and how much hydrogen one can produce using this reaction. Okay, and now whatever we do, we need material. Okay, so if you look at this PEC water splitting chamber, it contains one photoanode, it contains a cathode. Important is photoanode, because photoanode is actually the electrode which absorbs light. Okay, and therefore selection of material is extremely important. And we should always keep this solar spectrum in our mind. We have already discussed several times the solar spectrum. So this is the wavelength of light, and this is the radiation energy. So you can see this is a typical visible band, and this is 1.23 electron volt line. Why there is a line at 1.23 electron volt? Okay, and this is the rest of the energy. So in PEC water splitting, the 1.23 electron volt is extremely important. Why? The reason is that suppose I draw this line. Okay, so this is a chemical potential line along y-axis. It is as per standard hydrogen electrode, which you know in electrolysis, standard hydrogen electrode or normal hydrogen electrode. Okay, so I give two lines here. One line is for H2 production, or this is also known as HER line. So in PEC water splitting, how we have produced H2? We produce 4H plus plus 4E minus equal to 2H2. So this is the reaction. Okay, we produce hydrogen molecule or hydrogen gas. If I look at as per standard hydrogen electrode energy potential, then this particular potential is exactly at 0.0 electron volt. Okay, but water splitting also involves the oxygen production. So in another side we have oxygen by OER or oxygen evolution reaction. If we look at the potential for OER, you will see this is exactly at 1.23 electron volt. There is a gap, meaning the energy which minimum energy which is required to trigger an hydrogen evolution reaction and oxygen evolution reaction, there is one HER and one OER, is 1.23 electron volt, and therefore it is extremely important in solar spectrum. 1.23 electron volt photons is required. So that means I need a material if I look at in material perspective, I need a material or I need a photoanode whose band gap should be minimum, it may be higher also, about 1.23 electron volt. This is conduction band and this is valence band. Okay, so therefore my first choice of material depends on this particular energy, 1.23 electron volt energy. Okay, so I just continue with this material aspect. So I can choose about material in this manner. I have this is HER, this is OER, this is H2 production, this is oxygen production, and then I can have conduction band minima here, valence band maxima here. CBM stands for conduction band minima and VBM stands for valence band maxima. So I can have a situation here, or I can have conduction band minima here and valence band maxima here, or I can have conduction band minima here, or I can have valence band maxima here. This could be all choices of various material or semiconducting material. Okay, so I would like to have a choice which is this one. This conduction band minima should be slightly higher than the HER line, and valence band maxima should be slightly lower than OER line, so that we are above this potential 1.23 electron volt potential, and then we can trigger a water splitting reaction conveniently. So we have to choose material in such a way that conduction band minima and valence band maxima position in terms of standard hydrogen electrode potential. This should be the position of conduction band minima and valence band maxima. Okay, so the first thing which we have learned, and then we have seen how, you know, how this the material, the basic, the band cap or the band locations, CBM and VBM locations of a material is important. Okay, so in the next class we will see that how one can use a semiconductor material as one electrode and one metal as another electrode, or two semiconductor materials in N-type and P-type material, and then produce hydrogen. Okay, so for today, if we summarize what we have discussed, we discussed what is the importance of a green environment, and what is the importance of hydrogen, what is the role of hydrogen in order to have the entire the green energy, green economy, green environment. All right, and how hydrogen is actually plays a very important role in realizing this entire the green energy revolution. That is what we discussed. And then I also discussed about various processes very briefly that people are already using for hydrogen production, which are the fossil fuel burning, biomass gasification, and electrolysis of water. And then we have started a new hydrogen production, which is completely green hydrogen production, which is completely based on photoelectrochemical water splitting. So the advantage is that in electrolysis we need the input electrical energy. Here we don't need any electrical energy is input. We use sunlight as energy and split water and produce hydrogen by hydrogen evolution reaction and produce oxygen by oxygen evolution reaction. And then we discussed little bit about what should be the material, what material we should choose, say for photoanode. And what we have seen that as the potential difference between HER and OER reaction is 1.23 electron volt, therefore the CBM and VBM of the photoanode should be placed in such a way they are slightly more than 1.23 electron volt, so that they can conveniently split water and produce hydrogen and oxygen. Thank you.